Hi there, and welcome to the screencast on uncertainties and errors in measurement. This is a screencast in a series of screencasts on IB Physics. This is topic 1 about physics and physical measurement. So in this screencast, we're talking about uncertainties, how to appreciate and understand them, and where they come from. What the uncertainties are when you're measuring on analog and digital instruments, how to minimize uncertainties. We'll learn about precision accuracy. Random and systematic errors, how to combine uncertainties, and then how to represent uncertainties graphically. Let's get started. Well, errors and uncertainties happen, right? So this is a part of life, and we need to accept them rather than ignore them or what have you. So this is okay. So we need to be okay with uncertainties. In fact, IB really requires that we have uncertainties because they want to see if we can appreciate it and understand it. So every measurement, you're going to have some uncertainty. It's life. It's the real world. Why is that? Well, it could be the measuring device you're using. It's not very good. Could be the way you're measuring with it. Maybe you're doing something wrong or sloppy. Or the nature of the measurement itself. For example, the speed of light is really difficult to measure. So if you try and measure it with by however means, you're going to get some uncertainty in your result. So if you have an analog measuring device, and those are things that are, well, not anything that's non-digital. So for example, a watch, for example, or a clock that has the hands that are moving, in circular, on the circular dial. That's an analog clock. We're going to use plus or minus 1/2 the smallest scale division. Now this sounds a little confusing, but let's do an example. Okay, and this is going to be the best case. So if we have a ruler, this is an analog measuring device, right? And we have, let's say, right there. What would you say that value is? Would you say it's 4.2? And it looks like it's centimeters. What would be the uncertainty there? Well, according to this rule, we're going to take 1/2 the smallest scale division. So the smallest scale here, if this is 1 centimeter from 4 to 5, it's broken up into 10 divisions. So the smallest scale division here is 1/10 of a centimeter. And we're going to take 1/2 that. So 1/2 of a tenth, or 1/2 of 0.1, is plus or minus 0.05. So we would report this result to be 4.2 plus or minus 0.05 centimeters. All right? And we're going to always report our uncertainty to one significant figure in IB land. Okay. Another thing we're going to see is the number of decimal places need to be the same in both numbers. Now this is the best case, right? You would only go up from here. For example, if there were some other factors in your experiment that you thought made the uncertainty to be more than this, well, then you should go with that, right? Your opinion, your experimental technique, and your knowledge of it would trump this rule. So here's another example of an analog meter. It's a voltmeter. So any kind of meter with a needle that moves like this with a magnetic moment would be an analog meter. What would you say this value is right here? Well, I'll go ahead and pause your video if you want to take a stab at it. Okay, so the smallest division here looks like it's 1 volt, right? These are ones, it's 25. So 1 volt plus or minus 1/2 a volt. So we'd report this reading as 22 plus or minus 1/2 a volt. And here again, we want to have the same number of decimal places in our data value and uncertainty. And uncertainty to one significant figure. Let's try digital measuring devices. What's a digital? Well, these are meters that have like numbers flashing at you. And for these, we're going to use the smallest unit shown. That's also called the least count. For example, here's a digital voltmeter. And you can see this one is showing 19.16. So we're going to use an uncertainty of this decimal place over here, which is 0.01. So that's our uncertainty, plus or minus 0.01. Now, if you're taking measurements and you're doing the multiple trials, so you're taking the same exact measurement under the same conditions multiple times, we have a different way of calculating uncertainty. What we're going to do is find the average of all your trials when you do that. And the uncertainty is going to be 1/2 plus or minus 1/2 the range of your set of values. So you can have a maximum value for those trials, and you'll have a minimum. You take that range, and your uncertainty is plus or minus half of that range. Let's take an example of this. Say you go and measure a table, and you do it 5 times, and you get these results right here in millimeters. 1560, 65, 58, 67, 58. Well, the average value is 1563. We add them up, divide by 5, and we can find the average value. The uncertainty is we need to find the range, so we need to find the maximum. 67 looks like the biggest, and the smallest is 58. So we would subtract those two, find that range, divide by 2, you get 4.5 millimeters. So we report the length of the table to be our average, 1563, plus or minus, remember we must have one significant figure here, 5 millimeters. So this means that the true result could be anywhere within that range of 1558